Welcome to this full lecture. This is Arnold Rangakuramya from Kisembo Academy. In this full lecture, expect to see the following. I'll talk about charging by induction, then I'll go on and talk about the electrophorus, a device that is used to detect charge. Then I'll talk about the electroscope and how we use that electroscope to detect presence of charge. I'll also go ahead and discuss how we detect the magnitude of charge using a gold leaf electroscope. Then I'll go ahead and conclude with Faradays Ice pail experiment to show that no charge resides inside a hollow conductor. But before I get into the details of all those nitty-gritties, we'll first discuss the very basics of electrostatics coming up. Electrostatics is simply a branch of physics that deals with the phenomenon and properties of stationary or slow-moving electric charges with no acceleration. As we explore this topic, we'll start with the atom. So what is an atom? An atom is simply the simplest invisible particle of an element. It consists of a nucleus which is surrounded by electrons in their respective electron shells as shown in the diagram. Here, we shall explore a few aspects about the atom. Thanks for tuning in. It's Kisembo Academy. So looking at this diagram, we have the nucleus, we have the electrons, and these electrons are positioned on electron shells. These electrons are free moving. They are always rotating around this nucleus. In the nucleus, we have the neutrons and protons. These neutrons and protons combined together make the mass of the nucleus. It should also be known that the mass of an atom is concentrated at the nucleus, and these electrons have got a negligible mass. So when we want to find the mass of the atom, we simply compute the total number of neutrons and the total number of protons that are present in the nucleus. Now around the nucleus we have electron shells, and these electron shells have got free moving electrons that are always moving around. These free moving electrons are negatively charged. The protons that are found in the nucleus are positively charged, and the neutrons here do not have any charge. So the protons here are positively charged, the electrons are negatively charged, and the electrons are always free moving around the nucleus. In the first shell, the shell that is immediately after the nucleus, it has got a maximum of just 2 electrons, and in the next shells, the shells that come after the first one, have got a maximum of 8. When an atom is neutral, it means that the number of electrons that are rotating around this nucleus is equal to the number of protons that are inside. It means that the positives and negatives are the same. It means that that atom is considered neutral. Now, during bonding, these electrons that are always moving around the nucleus can be lost. Now, when an electron is lost during bonding, it means that the overall number of protons in the atom will be more than the overall number of electrons. It would mean that this atom has got more positive charges than negative. And so that means that overall, the atom will be considered a positively charged one. Likewise, during bonding, this atom can gain more electrons. When it gains more electrons, it means that we are having more negatives than positives. And so it means that overall, the atom will be considered negatively charged. Electrostatic electricity can be produced when you rub a plastic ruler or pen against hair sound, or when you iron a shirt. Sometimes it produces a cracking sound. That is electrostatic electricity being produced. Also, when removing a sweater, for example, you hear a crackling sound. When you hear the crackling sound, sometimes when you're removing a sweater, it means that is static electricity being produced. To be able to identify positive and negative charges will depend on what we use. For example, if a polythene or ebonite rod are rubbed by a duster, they'll become negatively charged. And if a glass rod or cellulose acetate are rubbed by a duster, they'll become positively charged. How to charge a body by induction? The word induction is a combination of two words, an English word called induce and a Latin word called inductio. Combining them together gives you induction. Induction as a word has varying meanings depending on the context. For example, it could mean that the process of formally introducing you into an organization, or in medicine it could mean the process of bringing a child birth by artificial means, or in mathematics it could mean proving a theorem by showing that it is true, and so on. But for this video we'll look at induction in the physics context as simply the process of charging a neutral body by the proximity of another charged body, with the two not being in contact. This is what we mean by charging a body by induction. It's Kisembo Academy. Thanks for tuning in. In the first case, we get to see how to charge a body positively by induction. And in our first diagram, we are having a body that is negatively charged, and we are having a conductor. This conductor is placed on top of an insulator. So this insulated stand is holding a conductor. As you can see, this conductor has got both positive and negative charges, so this conductor is neutral. This is a negatively charged body. So we get a negatively charged body, we place it near a neutral conductor. When a negatively charged body is brought near this conductor, it means that this being negatively charged, it will repel the negative charges. And when these negative charges are repelled, the positive charges remain attracted here. The negative charges are repelled away. So while this conductor is still in the vicinity of this conductor, while this charged body is still in the vicinity of this conductor, we ground this conductor, or we earth the conductor. And when we earth the conductor, the negative charges are further repelled to the ground. So when we break the earthing, or when we break the ground, we remove this and that at the same time, you will find that most of the negative charges were repelled to the ground, so the conductor remains predominantly positive. It means that this has been positively charged by induction. Charging negatively by induction, we'll do it like before. When we get a positively charged body and we bring it in the proximity or in the vicinity of this neutral conductor, these positive charges are going to attract those negative charges. So the negative charges will be attracted to this side of the conductor, leaving this side with more positive charges. So while this body is still in the vicinity of the conductor, we earth the conductor. When we earth the conductor, negative charges are attracted from the earth into the conductor. When they are attracted to the earth into the conductor, you will find that this body now starts gaining more negative charges as compared to the positive charges that are already there. So when you break this earthing and remove this charged body all at once, you will find that you have gotten a body that is predominantly negatively charged. And this is how we charge a body negatively by induction. How to produce two opposite charges from one type of charge? We are going to get two conductors and we are going to make sure they are in contact. These two conductors are positioned on insulators. So when we put A and B conductors, we position them. This is end A and end B. We bring a positive charge like before. We bring it in at the end, near end A. When we do so, these positive charges are going to attract the negative charges that are within these. Negative charges will be attracted towards end A, and so end B will have a net positive charge. When this happens, you separate these conductors while the charged body is still there. It's still in position. When you separate the two, you'll find that conductor B has a predominantly positive charge and A is negatively charged, and that is how we induce two opposite charges from using one type of charge. Now we should take note that in conductors it is only negative charges that flow. An electrophorus is a manual capacitive generator and as such is used to produce electrostatic charge by electrostatic induction. It has a metal disc and an insulating handle as shown in the diagram. In this video, we shall concentrate on how to charge the electrophorus by induction. It's Kisembo Academy and thanks for tuning in. So looking at this electrophorus with an insulating handle and a metal disc, it has also we have a slab of ebonite or cellulose acetate. If we rub a slab of ebonite with a duster, it will become negatively charged, and if we place this metal disc on top of that slab, then it means the charge that is on that slab will be picked by that metal disc, and then we shall remove that metal disc with that charge, whether positive or negative, and we will be able to use it later. So in our write-up we have that when the slab of ebonite is rubbed with a duster, it becomes negatively charged, and so the metallic disc is placed on top of the slab. When we place that metal disc on top of the slab, it means that that slab is going to pick up that charge. This is the slab we are talking about. This is the metal disc. So after rubbing this slab with the duster, it will become negatively charged. When it becomes negatively charged, we get our metal disc and insulating handle. We place it on top of this slab. When we place it on top of this slab, remember that this metal disc initially was neutral, and so when you place it on top of this slab, this being negatively charged, it means that it's going to repel these negative charges. They will move away. The negative charges in blue will be repelled towards the top of the metal disc, and the positive charges will remain predominantly here. So if we earth this metal disc, if we earth it or we ground it, it means that you're going to have these electrons flowing out of this metal disc into the earth. And so when we break this earthing and we remove this metal disc, you'll find that this will be predominantly positively charged, and in so doing we will have charged this metal disc. The electroscope is a device that was used by early scientists to detect the presence of the magnitude of electric charge on a body. Back then it was the first electrical measuring instrument. In this tutorial we shall talk about the parts that make up the gold leaf electroscope and how it is charged, both positively and negatively by induction. This is Kisembo Academy. Thanks for tuning in. As you can see in this diagram, we are having the electroscope, or it is sometimes referred to as the gold leaf electroscope. It has got a brass cap. This brass cap is connected to a brass rod, which is connected to a brass plate, and this brass plate has got the gold leaf. This leaf keeps flapping, it keeps diverting. It keeps diverging upwards or converging towards the brass plate downwards, depending on what charge is imposed on top. This gold leaf or electroscope also has got an insulator, and we have a glass window there, and all this is within a metallic case. So now, what exactly is the use of this? This device called the electroscope can be used to detect the presence of charge, the nature of the charge, the magnitude of the charge, and the insulating property of any substance. We'll be looking at those later, but from our write-up here, the device is used to detect the presence of charge, the nature of charge, the magnitude of the charge, and the insulating properties of a substance. A gold leaf electroscope, or an electroscope for that matter, can be charged in two ways. You can either charge it by contact or charge it by induction. In charging by contact, you simply place an electrophorus or any other charged body onto the cap of a gold leaf electroscope. Now, talking of an electrophorus, we did so in our previous videos. An electrophorus is simply a metallic disc that is mounted onto an insulating handle. So when we get this electrophorus and it is charged, when we put it on top of the cap of a gold leaf, the charge that is on that charged body simply is automatically transferred onto the electroscope, and that is how we charge by contact. So we will also explain how we charge a gold leaf by induction. We look at charging by induction negatively. How do we charge an electroscope negatively? If we want to charge an electroscope so that it attains a negative charge, it means that we are going to first introduce a body that is positively charged. We bring a positively charged body close to the cap of a gold leaf electroscope. This is the cap of a gold leaf electroscope. This is the brass rod, the brass plate, and the gold leaf. When we bring this positive charge, it means that it's going to attract the negative charges that are resident within this apparatus. So the negative charges will be attracted towards point A, and when the negative charges flow towards point A, it means that down here and around there, an excess of positive charges will be left. So it means that these areas will have an excess of positive charges as the negative charges are moving towards point A. Remember, as far as electrostatics is concerned, it is only the negative charges that move. Positive charges don't move. So this is our first step. We bring this positively charged body near the cap, and this is what happens. So when that happens, in the second case, we earth, while this body is still in position, we earth the cap of the gold leaf electroscope. So when we earth this cap, the electrons from the earth are going to flow. Remember, it's only electrons that flow, or the negative charges, not the positive ones. So the electrons will flow onto the cap. When they do flow, it means that we are going to have an excess of negative charges here. When these electrons flow into this cap, they are going to go ahead and neutralize the positive charges that are already here. So when these positive charges are neutralized, it means that the gold leaf electroscope here is going to collapse. When it collapses, we remove this and the earthing at once. And when we do so, it means that now there is going to be a net negative charge in the gold leaf, and so this will cause this leaf to diverge once more. And that is how we charge a gold leaf electroscope negatively by induction. So how do we do it positively? In charging a gold leaf electroscope positively by induction, we are going to do more or less the same thing. We are going to introduce a negatively charged body, and we are going to bring it close to the cap of the gold leaf electroscope. When we bring it close, this negative, because this is negatively charged, it is going to repel the electrons, or it's going to repel the negative charges here. So you're going to find that there's going to be a predominant positive charges at A, more positive charges at A, and the negative charges that will have been here will have been repelled to point B and towards the leaf. And so just like we did before, we are going to earth this cap while this body is still in position. So while the negative charge is still in position, we are going to earth this cap, and when this cap is earthed, electrons are going to flow from the cap to the ground. So when the electrons go to the ground, it means that we are going to have less electrons here and more positive in this setup. And so after doing that for some time, when you remove this and that at once, you're going to have this predominantly having positive charges, and so this leaf will diverge. So that is how we charge a gold leaf electroscope positively by induction. So in summary, there are two ways an electroscope can be charged. It can either be charged by contact or by induction. In charging by contact, we do so by placing a charged body like a metal disc of an electrophorus on top of a cap of a gold leaf electroscope. This transfers the charge onto the metal disc onto the electroscope. In charging by induction, the procedures are more so similar onto how we charged a conductor by induction, as illustrated in the previous tutorials. The diagrams we have just explored show the process of charging the electroscope by induction. How to use an electroscope to detect the presence of charge. Like earlier said, we use an electroscope to detect the presence of charge on the body. This tutorial serves to show how this is done. This is Kisembo Academy, and thanks for tuning in. So we shall simply follow this table and we'll look at the observation and the sign of the charge that should be after making that observation. Let's look at this diagram here. This is the cap of a gold leaf electroscope. It's called the brass cap. This is the brass plate, the brass rod, the brass plate, and the gold leaf. This is a positively charged gold leaf electroscope. Now, let us introduce a body on top. If we introduced a body on top of this near the cap of this gold leaf electroscope, a positively charged body, what will happen? Because this is a positively charged body, it means that it is going to attract negative charges from down here up there. So when these negative charges are attracted to come up here, it means that there's going to be an excess of positive charges down there. And the excess of positive charges down here is what is going to cause an increase in divergence. And so it means that if we are having a positively charged gold leaf electroscope with this kind of divergence, then we introduce a body and the observation is such that there is an increase in divergence, then it would mean that the body that will have been introduced will be the same charge as the gold leaf, which is positive. So that is what happens for the case of a positive charge. If we are having a negatively charged gold leaf electroscope and we attempted to introduce a body on top that is also negatively charged, what will happen? This negatively charged rod is going to repel negative charges that are on top here to come down here. So it means that the negative charges, upon being repelled, will create an excess of negative charges at the brass plate and at the gold leaf, and this will cause an increase in divergence. So that means that if you're having a negatively charged gold leaf electroscope like this one, and you introduced a body near the cap, and it is such that, and what happens, the observation is that there's an increase in divergence, then that would mean that the body that has been introduced at the cap of the gold leaf has got the same charge as the gold leaf electroscope, and that explains our first table. Our first table is saying that an increase in divergence, if that is the observation, it would mean that the sign of the charge of the body that has been introduced is the same as that on that electroscope. So now, let's examine the second case. At first, we are having a negatively charged gold leaf electroscope. So we introduce a body that is not negatively charged but positively charged. What happens? When we introduce a positively charged body, these positive charges are going to attract the electrons from down here. So it means that the electrons that were formerly here are going to be attracted to come and concentrate up here by this positive charge. So when that happens, it would cause the divergence of this leaf to drop. And so what does that mean? It means that if you're having a negatively charged gold leaf electroscope and you introduce a body whose charge you do not know on top, and the observation is such that the divergence of this gold leaf drops, it would mean that that body has got a positive. If the gold leaf is negative, it means the body is positively charged, like I have explained. Likewise, looking at a positively charged gold leaf electroscope, it is positively charged, the brass plate is positive, the gold leaf is also positively charged. But if you are to introduce a body at its top, a negatively charged body is introduced at its top, the divergence of this leaf is going to decrease. Why? Because when you introduce a negatively charged body at the top, the negative charges that are at the cap are going to be repelled away from this place. So they will be repelled towards the brass plate and the gold leaf. So since originally down here they were predominantly positive charges, when the negative charges that are on top are repelled downwards, they are going to neutralize the positives that are there. And when they are neutralized, it means that the divergence of that gold leaf will be decreased. So what does that mean? It means that if you're having a positively charged gold leaf electroscope and you introduce a body whose charge you do not know, and the observation you make is that the divergence decreases, then you just know that whatever body you have introduced there has got a sign or a charge whose sign is opposite the sign of the gold leaf electroscope. And that explains our second assertion, that a decrease in divergence means that the sign of the charge that is on top of the cup is opposite, is the opposite, or the opposite sign as that on the electroscope. Besides finding the nature of the charge of a body that is brought on the cup of a gold leaf electroscope, an electroscope can also be used to detect the magnitude of the charge. And detecting the magnitude of the charge is as simple as looking at the level of divergence of the gold leaf. If the gold leaf diverges very highly, it means that the magnitude of that charge is high. And if the divergence is not as much, it means the magnitude is low. So in our write-up here, we are saying that here we compare the level of divergence. A higher divergence of the gold leaf shows a higher magnitude of charge. A gold leaf electroscope can also be used to compare the insulating properties of a substance. So, in our write-up here, we say that different substances are put on the cap of a gold leaf electroscope. When the divergence of the leaf falls, it shows a good conductor of electricity. And if there is no effect on the gold leaf, it shows a bad conductor of electricity. Faraday's ice pail experiment. In Faraday's ice pail experiment, we'll only show that there is no charge residing inside a hollow conductor. It's Kisembo Academy, and thanks for tuning in. This is the gold leaf electroscope. It has got a cup, a brass rod, a brass plate, a gold leaf, a metal casing, and an insulator there. This is the apparatus. Now, to begin with the experiment, remember we said that we are carrying out this experiment to show that no charge resides inside the hollow conductor. So sphere B is put inside an ice pail, but while we put this sphere B inside this ice pail, we do not allow this sphere to touch the walls. We just leave it hanging. So now when we put this sphere and we leave it hanging in space, what exactly happens? Because this is a sphere that is positively charged, and then it is this setup is put on a gold leaf electroscope that is also positively charged. So what exactly happens when this sphere is in here? Now sphere B being positively charged is going to induce a negative charge around. Now this negative charge that has been induced inside the ice pail as a result of this positive charge is also going to induce a positive charge outside the ice pail. Of course, it can't induce a negative charge. It definitely has to induce the opposite charge. So the negative charge inside the ice pail induces a positive charge outside the ice pail. So outside the ice pail, we have a positive charge that is induced all over. So now, because of this positive charge that is induced outside the ice pail, this positive charge is going to attract electrons or negative charges from down here. And so negative charges are going to be attracted from the gold leaf, and they are going to come and concentrate more here on the cup, like as it is shown. So since electrons have been attracted, or negative charges have been attracted up there, it means that you're going to have more positive charges down here. And so because you're having more positive charges on the brass plate and at the gold leaf, this divergence will increase further. Why does it increase further? Because now the magnitude of the positive charges has increased. Remember, the laws of electrostatics state that like charges will repel. That's why they repel. But if these were unlike, they would attract. So that the divergence will increase. So now when this divergence increases, it simply shows that the charge behind outside this ice pail is actually the same as the charge that is on the electroscope, which is positive. We now let sphere B to touch the walls of the ice pail. When we let sphere B to touch on the walls of the ice pail, and then we later remove this sphere and we test for the charge, we will find that there is no more charge on sphere B. Initially we had put it in when it was positively charged, but when we let this sphere B to touch, when we let it touch the walls of the ice pail, then we remove it and test for the charge on B, we will find that B does not have any charge. Now why does that happen? It's no longer having a charge, but the divergence of the ice or the gold leaf is still remaining the same. So the question is that why is it that sphere B, which was initially charged, is no longer charged? And the only way you can explain this is that this is because when the sphere was allowed to touch the inside of the ice pail, the inducing charge outside the sphere, this inducing charge, the inducing charge outside the sphere was neutralized by the induced charge inside the pail. This shows that the inducing charge outside the sphere and the induced charge inside the pail are equal in magnitude. Therefore, this proves to show that no charge resides inside a hollow conductor. And that's it for Faraday's ice pail experiment. Please do not forget to comment below or hit that like button. Someone out there might like to watch this tutorial. Don't forget to share. Otherwise, for more videos, simply subscribe to this channel. For Kisembo Academy, this is Arnold Rangakuramia.